In today's video, we're going to cover a topic that's been requested for quite some time, and that's to look at the fundamentals of IQ signals or quadrature signals, including IQ modulation and demodulation. Now, to present this right, we need to understand a couple of concepts kind of in order. Just the basics of a sine wave, what makes up its amplitude, frequency, and phase, and then how we can represent amplitude modulation of that sine wave as well as frequency and phase modulation. We'll talk about what quadrature signals are. It's actually a very simple definition. And then what happens when we add quadrature signals together, and that's kind of the key to the whole thing. And then how we can use all of this to modulate, demodulate, process, and analyze IQ signals. Now this should be review for everybody, just the components of a sine wave. A sine wave has got a certain amplitude, we'll call that A, and then basically just follows this shape here, using the sinusoid function, 2 pi times the frequency, which is 1 over the period, times time, plus some offset in phase if we wanted to shift this waveform back and forth. So, very simply, if we're going to modulate this waveform, the properties that typically can get modulated are the amplitude, the frequency, or the phase. And that's amplitude, AM, FM, or PM type modulation. And just about all modulation types are really just functions of those three things or combinations of those three things. So just focusing in on amplitude modulation, all we're essentially doing is taking that amplitude term and making it some function of time, maybe like a slowly varying sine wave, and using that to multiply against the sinusoid function. And what we do is basically modulate or change the amplitude of that sine wave in response to that baseband signal. Now normally the modulating envelope, if you will, the baseband signal is much slower than the carrier, so you really can't see that. And if you looked at something on the scope, it might look kind of like this picture here. We'll actually go take a look at it on the scope. Here's an example of just a live sine wave at 10 megahertz shown on the scope. We can see a couple of cycles of it, see its amplitude and its frequency. And if we add some amplitude modulation to that, we can kind of see it varying up or down. If we slow this down so we can actually see the baseband envelope, and I'll change the trigger to be synchronous with my baseband signal. And now we can actually see the amplitude of that signal varying in response to a lower frequency baseband. And that's what's essentially very common with amplitude modulation of RF signals, is that the variation of the amplitude component with respect to the RF component is typically much slower. And that's very typical of what you'd see of the envelope of the RF signal for amplitude modulation. Okay, so now that we know essentially the components of a sine wave, what it looks like, and what it looks like when it's amplitude modulated, let's add another concept here of what are quadrature signals. And it's actually pretty simple. Basically the definition is that if two signals are 90 degrees apart in phase, they're said to be in quadrature. Very simple, just a quarter cycle. In fact, a cosine wave and a sine wave are quadrature waveforms. You can actually see them both plotted here. The black waveform is a sine wave and the pink waveform is a cosine wave. We can see that they're separated by a quarter cycle or 90 degrees. So they are quadrature waveforms. Each one of them can obviously have its own amplitude. And essentially for quadrature waveforms, what we do is we basically say that the amplitude of the cosine wave, we call that I, or the in-phase signal. Okay, so that's I times the cosine of 2 pi ft, maybe there's another phase, there wouldn't be another phase shift in this case. And then the amplitude of the quadrature waveform, or the sine waveform, is Q. So that's kind of given by this definition here. So Q times the sine. So since these are 90 degrees out of phase, these are quadrature signals. So since all of the argument here is going to be the same, they're identical waveforms that just shifted by 90 degrees, the only thing we really need to know are the I and Q values. And if we start changing the I and Q values versus time, we'll change essentially the resulting sum of these two waveforms. So let's take a look at what happens when we add these two waveforms together and some of the cool properties associated with that. Now the adding of quadrature signals is really kind of the key for all of the quadrature modulation we're going to be talking about. So let's look at the example here. I've got a cosine wave and a sine wave, so the I and the Q waveforms. If those two amplitudes are equal, we're going to get a resulting sum of those that's going to have a phase shift that's midway between them, or about 45 degrees. Okay, if we assume that one's 0, this one's 90, this one's going to be 45. Now if the magnitude I and Q are varied in the same direction at the same time, it'll make these signals bigger or smaller. The resulting sum will just be bigger or smaller. So, very simply, we can amplitude modulate the sum by amplitude modulating the I and Q waveforms in an identical way. Now let's look at what happens if we don't vary the I and Q components in an identical way, if they're varied differently. So let's look at an extreme. Let's say we had I equal to 1, okay, but Q equal to 0. So that takes that out of the picture. So the sum is just going to be the I waveform. So it's just going to look like the cosine wave. So this waveform shifts over, by 45 degrees. Similarly, if we made I equal to 0 and Q equal to 1, the output would look like the sine wave, would shift this way, a full 90 degrees from the cosine wave. So we can see by varying the I and Q differently, we can actually cause a phase shift or a phase modulation of the resulting sum. Now, of course, frequency modulation is just a form of phase modulation, so that works as well. So you can see by appropriately varying the I and the Q as a function of time, we can cause the resulting sum of those waveforms to have amplitude modulation, frequency modulation, phase modulation, or really any combination of all of that. So through simple amplitude modulation of I and Q, we can create complex modulation in the resulting sum. And that's really the whole key with IQ modulation and IQ signals, and why they're really used in modern software-defined radio and a lot of other applications. So let's take a look at that using some math on the scope. So I've got putting into the scope here two 10 megahertz sine waves that are in quadrature. You can see the 90-degree phase shift between the two. And if we add them up using the math waveform here, just change the scale of that, we can see the resulting sum, and it's shifted in phase with respect to these two. It's right in the middle. Now if I knock the amplitude of one of these down to 0, we can see how that waveform shifted in phase. Okay, if I bring that waveform back up and turn the other one to 0, you can see that waveform shift in phase again. So we can see how varying the amplitudes in a different way will cause a phase shift. And of course, if we vary the amplitude of both of these signals, like if I vary one signal and bring it up in amplitude, we can see that that sum's coming up. Well, we're getting a little bit of a phase shift because they're now different in amplitude. We switch to the other waveform and bring its amplitude up by the same amount. Okay, now we can see that signal is shifted back in phase and the resulting sum is big. So we can see how we can get a phase modulation as well as an amplitude modulation by varying the magnitude of I and Q. And again, that's really the whole key. We can do very complex modulations by simply doing amplitude modulation of I and Q waveforms. Now, another way to visualize or represent IQ signals and the resulting sum of those signals is a diagram called a phasor diagram. And this can be really useful for certain modulation types. And the way a phasor diagram works is this. The amplitude of a signal is basically represented by the length of this vector, going from with the center representing 0, and the longer that arrow or that vector is, the higher the amplitude of the signal. And then the phase of the signal with respect to 0 degrees, like a cosine, is represented by the angle, okay, of that ray starting from the center. So it really is kind of a representation of the I and Q components. So let's look at what I mean by that. Let's say when the I and the Q components are equal, like I have here. I is equal to 1, right? And Q is equal to 1. So I have an I value that's equal to the Q value. The resulting sum of those gives me this vector in this dimension. You can see I've got about a 45-degree phase shift as opposed to, say, 90 or 0. So I can see I've got that 45-degree phase shift, and I can calculate out with simple geometry, essentially what the magnitude of that waveform is, right? It's the square root of I squared plus Q squared, okay? So I can actually see everything about that signal by looking at the phasor diagram. For example, if the Q was brought to 0, the Q component went to 0, then this waveform would come all the way down here, and all we'd have left is just the I component. Similarly, if I is brought to 0, then the waveform would go all the way up here. The ray would go all the way up here. We'd have a 90-degree phase shift, and the amplitude would just be the Q value. So we can see the phasor diagram can be really useful to represent both the I and Q components, right? The amplitude of those two I and Q waveforms, as well as what the resulting sum is doing. This type of phasor diagram is very often used to help visualize many different digitally modulated RF signals, because oftentimes the digital modulation is going to be forcing the carrier to be going to certain amplitude and phase combinations to represent a given symbol or set of bits. So let's walk our way into that a little bit. Let's look at one of the simpler digital modulation types, or BPSK, binary phase shift keying. And that's essentially where the phase of the carrier is just altered between, essentially 0 degrees and 180 degrees, essentially inverting the waveform. So from an IQ standpoint, it's actually very simple. Either I or Q could be set to 0, and then the other one varies between +1 and -1. And that essentially just inverts the waveform. It's like multiplying by, remember, this is the amplitude of a cosine wave. So we multiply it by +1, we get this. We multiply by -1, the signal just inverts itself. So let's go look at that signal live and see what I mean. Okay, so here's what that looks like with some real signals. I'm just using a mixer here to take a 10 megahertz RF signal and a 1 megahertz square wave that varies between essentially a plus and minus value, and using that to modulate the RF signal. So here's my 10 megahertz RF signal. Here's my square wave that's going positive and negative, and you can actually see the phase shift of this RF signal now, essentially going from being in phase with the carrier to being 180 degrees out of phase with the carrier, back in phase again. You can actually see the phase reversals occurring at each of the digital signal transitions. So that's a simple way of creating or representing essentially a BPSK, phase modulated RF signal, by simply varying the amplitude, the I or the Q component of a quadrature waveform pair. Now, of course, on the phasor diagram, this will be represented by a signal that varies between this and rotating around to this. So essentially going from here to here to here, bouncing back and forth, between those 2 points, between essentially 0 degrees and 180 degrees, back and forth. Now, of course, if we take that, the next logical step is, let's say we vary not only the I between plus and -1, but how about we vary the Q between plus and -1? And we, basically quadrature modulate those, take a quadrature carrier, 0 and 90 degrees, multiply them together. So essentially we have one of these sitting here and one of these sitting here. The difference is that these two waveforms will be 90 degrees offset. And what happens is, when that happens, is you wind up with 4 combinations, right? You have a combination when they're both 1, and we saw that earlier when we first started talking about summing IQ waveforms. The resulting output is at 45 degrees. Now, if the I is -1 and the Q is 1, the phase shift would be 135. When I and Q are both -1, the phase shift will be 225. And then when I is +1 and Q is -1, we'd have 315. Now, if we look at that on the constellation diagram, that's kind of the one that was kind of plotted out here. So these 4 constellation points kind of represent, positive I and Q, negative I, positive Q, negative I and Q, and then negative Q, positive I. Those 4 constellation points. And that's what they're called, constellation points. So if we looked at a QPSK signal in this constellation diagram, we ideally have 4 points representing essentially those 4 combinations of I and Q. And so that's why this is a real nice handy way of looking at many of these quadrature or QAM modulated RF signals. So I put together this little bit of an assembly here to kind of show the QPSK modulation. I have a pair of mixers. Each of them is doing essentially that BPSK modulation. They're being fed with carriers that are in quadrature, and I've got them fed with digital signals to create the modulation. So let's zoom in on the scope screen and see what we've got. So if we zoom in here, we can see that here's my digital signals here, and they're varying. Both of them are varying between, essentially a negative and positive value. So they're both negative, and that one's negative, this one's positive, that's positive, and then this one is positive and that's negative. So those are the four states that we talked about, and you can actually see how that's now affecting the carrier. So we're jumping a quarter cycle from here to here at that transition. We're maintaining in that phase, and this transition is jumping us another quarter cycle, and so on. This transition is causing another quarter cycle jump. So this is what the carrier looks like and how the phase changes for a QPSK signal. And of course, that would be represented by those four constellation points, equal amplitude, okay, in all four states, but a different phase in all four states. Of course, there's really just two more aspects of this. The I and Q signals don't necessarily have to just be ones and zeros or plus ones and minus ones. They can be essentially any analog value. As we discussed earlier, we can essentially create amplitude, frequency, or phase modulation by simply amplitude modulating these quadrature carriers. So really any modulation type, AM, FM, PM, single sideband, double sideband, BPSK, QPSK, whatever it might be, any modulation type can be represented by the appropriate generation of I and Q waveforms. And this is a very common thing in software-defined transmitters, because these baseband signals are relatively low frequency and they can be synthesized very easily in hardware, and then or even in software, and then fed to a D to A converter, for example. Even all of this processing many times will happen digitally. So we can create any RF signal with just simply quadrature carriers and the appropriate I and Q. Of course, all this works in the opposite direction just as well for demodulating signals. Essentially, if you take any RF signal and then demodulate it with quadrature local oscillators to create the I and Q data streams, there is enough information in the I and Q to fully demodulate that signal, whether you're doing it for receiving the signal, to listen to it, or to grab data out of it, or to analyze the signal. Once you've got a signal represented by its I and Q components, you know everything there is to know about that signal. And again, this is the basis again for most software-defined radios, or SDR, because all these IQ signals can easily be generated or analyzed in software and processed through ADCs and DACs and things like that. For a lot of common low-cost software-defined radios, the sound card is actually used as the ADC and DAC, and then the samples from the sound card in a computer are used to modulate signals and demodulate signals. I hope you enjoyed this little tour through IQ signals and what IQ and quadrature signals are, how they can be used to modulate and demodulate signals, and what's meant by things like constellation diagrams when we're talking about digitally modulated RF signals. If you like what you see, please subscribe. If you have any questions, certainly put them as questions or comments in the video here. And thanks again for watching, as always.